Can you all see this perfectly? Wonderful. All right. Thank you so much, Diana, for that wonderful introduction. And welcome everyone to my chemistry senior experience talk titled Beer, More Beer, How Science Directs the Future of Brewing. And I want to start with giving you guys an idea what this talk will be about. So this talk is going to focus on myself, which sounds really selfish, but it's my chemistry senior experience talk. So why not focus on me? And I really have two passions, one being chemistry and the other one being beer and brewing. And for the majority of my life, I really did not know how deeply these two fields were connected with each other. In fact, the overlap between these two fields results in a new field, the field of brewing chemistry. And honestly, I had no idea that this field even existed until roughly 1.5 years ago when Alison and Bobby introduced me to it. But luckily, through my time at Lawrence, my views really have changed and my understanding of chemistry and brewing greatly were impacted. And now I'm planning to pursue a career in the brewing chemistry field. So, my talk will be about the science and chemistry behind brewing. But for us to understand the importance of science in the brewing field, we first have to get an understanding of beer itself. What is it made of, and what goes into it? So I will provide you guys with a small Brewing 101 talk. And with that background knowledge, I will explain to you the science behind brewing, how science has advanced the field in the past, and how science directs its future. So let's get started. When it comes to ingredients, beer can only be made out of 4 ingredients. So there's malt, hops, water, and yeast. And this dates back to 1516, when a Bavarian king introduced the world to this famous German law called Reinheitsgebot, which states that only these 4 ingredients can actually be used in beer. And each of these individual ingredients has its own purpose. There's malt, which is processed barley grain that contains starch, enzymes, and flavor compounds. There's hops, which is the flower of the female hop plant, which we use to make our beer bitter. There's water, which we use as a solvent because we want to drink it. And then there's yeast, or microorganism that we use to ferment our beer and it produces ethanol. And if we all throw them together into a pot, mix it, heat it, stir it, we get this liquid gold known as beer. Unfortunately, just throwing them together in a pot really does not do much. In fact, brewing is a little bit more complicated than that. So before I want to go into more detail, here's a small overview of the brewing process. So we first start with mashing, where we have the goal of producing a sugar water solution. So what we do here is that we mix malt and water together, heat it, such that we can dissolve the starches in the malt into the water. Following that, we will boil it. And this is where we add the hops to it and we make bitter sugar water. And finally, fermentation. This is where the yeast comes in, which produces alcohol, and we are ending up with beer. So let's dive a little bit deeper into mashing. So here we have a pot, and we add water to it, and we heat this water to a certain temperature. And with that, we can add our malt to the water, and we stir everything around. And the reason why we do that is because we want to dissolve the starches into the water. And these starches are very complex, long-chain carbohydrates. And not only do we want to dissolve them into the water, but we also want to break them down into smaller sugars. And for us to understand how we can break down the starch into smaller sugar units, we have to look a little bit closer into the malt itself. So here's our malt. And when it comes to brewing, we really care about 3 main things in the malt. So there's starches, there's amino acids, and then there's enzymes. And starches, again, are complex carbohydrates. They're hard to digest for most organisms. In fact, yeast cannot even consume it at all. And that is why we have to break down the starches into sugars, such that we can have fermentation occur. Then there are amino acids, which are important for the yeast growth. The yeast needs to produce proteins, etc. So we need to have amino acids present in our beer. And these amino acids also engage in certain chemical reactions that produce certain flavor compounds that are important for a beer. And then finally, we have enzymes, and these enzymes are the key to the breakdown of the starches into the sugar. And these enzymes get produced in the process of converting barley grains into malt, which is when they're, and what how it works is that they're basically stored under certain conditions, which allows the the barley grains to produce these enzymes. So basically, how we can picture the whole thing is that we dissolve our starch that come from the malt into the water, and we also dissolve these enzymes. And here we have our starch, and basically, the enzymes have the ability to break down the starch into smaller molecules. Essentially, they act like scissors, and they cut apart the starch into smaller sugar molecules that the yeast can then consume. The significance of this reaction is that without it happen, there's no fermentation going on, meaning that we don't produce any beer. In addition to the enzymatic reactions, there's much more going on during the mashing process. In fact, we can think of the brewing pot as basically being a very, very big reaction kettle with a great number of reactions occurring. And one of these reactions is the Maillard reaction. And we have all experienced this reaction because this is what happens when you toast bread and you will get this nice toasty flavor. This is what happens when you put in a steak into a pan and you get that brown crust on top of it. And with this reaction, we really start to dive deeper into the brewing chemistry, in particular into the flavor chemistry aspects of making beer. So the Maillard reaction involves sugars and amino acids, which both come from the malt. And when we dissolve them into the water and we heat them up, we allow them to react with each other. And they form melanoidins, which are these large brown polymers. And because there are plenty of different sugars and amino acids present, there's a great variety of different products that can form for this reaction. And the reaction that is shown on the slide is the reaction between glucose reacting with the amino acid asparagine, forming an acrylamide, which most people know as being bad for human people. So each of these products that is formed through the Maillard reaction has its individual flavor, and they all sort of add up to the complexity of the overall flavor of the beer. And for some beers, for example, a Doppelbock, these melatonins are something where we really want to see in our beers, as they give the beer this really nice, bready flavor. So we have done our mashing now. We have dissolved the starch and broke it down into small sugars. We had the Maillard reaction. Our reactions occur and form flavor compounds. So essentially what we have done so far is making sugar water. But before we do anything else, we have to actually remove the leftover grains. So now we are left with this sugary solution, and the sugary solution in brewing terms is called wort, which is essentially just another term for sugar water. So following, what we do next is that we will boil it. So we have our sugar solution, we start heating it up, and we are bringing it to a boil. And there's really two reasons why we do that. We first want to sterilize it, and we want to make it more bitter. The sterilization is important because we want to kill off all of the bacteria that are potentially in our solution, preventing any sort of contamination, because bacteria normally produce off-flavor compounds and therefore result in bad tasting beer. Passively, we are also killing off all of the enzymes that were involved in the mashing process, basically as a quality control point, such that they cannot further break the starch down. In addition to the sterilization, we want to make our beer more bitter, and this is where we add our hops to it. And the reason why we want to add our hops to it is because our sugar solution does not really taste very pleasant. It's far too sweet, and it's sort of like unbalanced. And you might ask yourself the question, why do we add the hops during the mashing, during the boiling, and not doing the mashing? And this really comes down to what hops is made of. So hops contains two big groups of flavor compounds. There's alpha acids, which cause the bitterness, and there's hop oils, which are terpenes. They consist of 10 carbon atoms, and these molecules can have various flavor compounds. The one shown is limonene, which is like essential the lemon flavor and lime flavor. And these two groups of compounds add to the complexity of the beer's flavor. But alpha acids are actually not bitter at all. So why would we add them during the boil? And there's something that happens to these alpha acids when we add them to the boil. By adding them to the boil, we're exposed to heat. And what happens with them is that they get isomerized, meaning that there's a structural change. And they undergo isomerization going from alpha acids to isoalpha acids. And in the example of humulone, we see a change from a 6-carbon central ring to a 5-carbon central ring. And this structural change causes the isoalpha acids to be bitter and soluble in water. And here's a fun story. So last summer, I brewed a beer at home, and I added the hops way too early in the boiling process. And because it's a chemical reaction, the isomerization of the alpha acids, it's kinetics dependent, meaning the earlier you put it in, the more isomerization you will have. And I ended up with a way too bitter beer simply because all of the alpha acids were isomerized into isoalpha acids. So we're almost done. So we made bitter sugar water. So far, we have boiled our sugar solution, we had added hops to it, we had our isoalpha acids, and now it's bitter. But there's one final step left, fermentation. And this is where our yeast comes in. So yeast is capable of eating our sugars and producing ethanol and carbon dioxide during the fermentation process. But in fact, yeast can do much, much more than only producing ethanol and carbon dioxide. And the yeast metabolism is much more complex than only one reaction. And through the yeast metabolism, the yeast produces a lot of different fermentation byproducts. And a lot of these fermentation byproducts actually have flavor compounds that end up being in our beer. I just want to point out a couple of ones. We have monoterpenes that have like lemon flavors. There's esters that taste like bananas. There's aldehydes that give you a really grassy flavor. And these are all compounds that we sort of want in our beer. They are very pleasant. And then there are the fermentation byproducts that are more unpleasant. There's hydrogen sulfide, which tastes like rotten eggs. There's diacetyl, which tastes like buttery popcorn, and we really don't want them in there. And the cool thing about yeast is that each individual yeast strain produces these fermentation byproducts at different concentration, giving each yeast strain its unique flavor profile. So by varying yeast, we can make different sort of flavored beers. So when we introduce our yeast to a bitter sugar water, it's actually quite shocked. It's not used to its new environment, so it has to like sort of acclimate. But once it realizes that it's surrounded by lots of sugar, it is super happy, and the yeast cells are multiplying on exponential scale. But at some point, there just isn't enough space anymore, and we have a final population. Unfortunately, this is where the life of the yeast takes a drastic change, because there's not enough sugar to feed the whole yeast population, and the yeast dies off. Sad for the yeast, good for us, because what that means is that fermentation is over and we have transferred a bitter sugar water into beer. So here we are. We have a fermenter full with beer. And this is the final step of the beer. So we only have to add CO2 to it, put it into cans, bottles, kegs, or any other sort of objects, and we are done. So where we've gone so far, we went from malt, water, hops, and yeast to packaged beer. So what is happening next? Let me demonstrate. So here's me. I just finished my capstone presentation. I'm super happy and I want to celebrate. And I go to the supermarket and I buy a bottle of beer. And this is my favorite beer. Just a hint, this was a tiny joke. So I open the beer and I start drinking it. And unfortunately, the beer just doesn't taste right. It's not what I'm used to, and I'm sort of like disappointed. I throw away the bottle of beer, and I decide to probably to not buy this bottle of beer again or this brand. And this is what makes brewing so hard. So the challenge of brewing is really to make the same beer over and over. We have to fulfill the flavor expectations of all the customers, particularly for big breweries who brew all across the globe. They have to somehow manage to make the same beer in different places across the globe. And what makes it so challenging is that each location might have slightly different ingredients. And to just give you an example, if we look at the brewing water, the water that we use to make our beer, there might be drastically differences in the ion concentrations that could potentially impact our beers. As an example, Appleton has a very low concentration of ions in its water. Now, if the local brewery, McFleshman's, would expand and open a brewery in Colorado, the water conditions would be very, very different, meaning that the brewers would probably have to change their recipes by just a little bit. And this is where we really introduce the concept of quality control in brewing. And I want to explain quality control with a very simple example. Let's picture that we are a Lego company and we make Lego pieces that are 2x2 and wet. So now I'm a quality control manager there, and I go into a local Lego store and I buy a set of our Legos. And I would expect that all of our Legos that I buy there are 2x2 and red. Unfortunately, what I figure out is that roughly 25% of the Lego pieces in the box are 2x8 blue pieces. And this is something that really can't occur. And it really does not matter if the customer likes the Lego, because we set ourselves a goal to only make 2x2 red Lego pieces, and we can't allow any variation at all. So, how does quality control look in the brewing field? So, brewers look for certain physical and chemical characteristics in beer, and these normally involve pH, alcohol content, color, turbidity, and my favorite, shape and size of bubbles. So, based on these characteristics, breweries and brewers define their golden standard. This is the product that they want the consumer to receive every single time. So, whenever brewers brew a beer, they will check if the beer that they just made fulfills the expectation and if there's no differences between their golden standard and the produced beer. And all of this quality control simply wouldn't be able without science. And over the past, science has significantly improved the quality control of brewing. And it all started out with the invention of the density meter, which is a tool that we can use to determine the density of a liquid. And this tool allows brewers to measure how much starch got dissolved into the water during the mashing process. But it also allows us to measure changes in the densities that occur when the sugar content decreases during the fermentation as a result of the yeast consuming the sugar. And with that knowledge, we can actually determine the alcohol content of our beers and see if it's consistent or not. In addition to the density meter, the pH meter and thermometer were big steps for the brewing world. Because all of our brewing steps involve enzymes, we need to have optimal pH and temperatures to have optimal conditions to ensure that the proper brewing process is achieved. So we have our goal, and our goal is how can we make the best beer possible? But we also not only want to make the best beer, we also want to make it on a consistent base. And the way we make consistent high quality beer is by carefully controlling every aspect of the brewing process and providing optimal conditions for the reactions to occur. So here we have our mashing process. And mashing works best when the pH is roughly 5.2 and we have 65 degrees Celsius. And we're dissolving our starches into our water and we are breaking down the sugar. And we can monitor how much starch got dissolved into a solution by using the hydrometer and measuring the gravity, which is essentially just the amount of dissolved sugar. But let's assume that we did not reach ideal condition. Instead of a pH of 5.2 and the temperature of 65 Celsius, we have a pH of 6.5 and a temperature of 55 degrees Celsius. So we check our gravity with our density meter, and nothing has changed at all. We still got the same gravity reading, so we dissolved all of the starches as expected. And everything looks normal so far. But we put it into a fermenter, and nothing is happening. The yeast doesn't eat the sugar for some reason. And with no fermentation occurring, we're not making any beer, which means that we wasted a lot of money. And this is exactly what we want to prevent. This is why we have to control all the conditions. So what did not happen here was, due to the unoptimal conditions, we did not break down the starch into smaller sugar molecules. And with that, our yeast, who's supposed to eat our smaller sugar molecules and to produce ethanol, actually never did that. So we want to control all of the conditions every single time we brew using our tools. So here are our basic tools. And these tools really can be used by anyone. You really don't have to be a scientist to understand how they work. And a lot of home brewers have them in their kitchens and are able to use them. But now picture this. We are a very, very big brewery that produces millions of gallons of beer per year, and we got a lot of money. So we tell ourselves that we want to step up our quality control game. And we set ourselves a goal to analyze the concentrations of 50 different flavor compounds in our beer that we believe are essential part of a flavor of our beers. Unfortunately, density meters, pH meters, and thermometers just won't do that. So what we need is some fancy chemical instrumentation. And this is where brewers sort of hit their limitation normally. Brewers are very good at making beer, and they also have a great understanding of basic chemistry. However, they don't know enough chemistry to use all of these cool tools that we potentially can use to analyze beer. We really need a chemist. The problem is that chemists only know chemistry, and they don't normally know much about brewing. So a brewer isn't a chemist, and a chemist isn't a brewer. But earlier I told you guys that there's this field, brewing chemistry. And I mentioned that there's a nice overlap between brewing and chemistry. So here we have Shane on the left representing the brewing fields, and on the right we have a lovely analytical chemistry professor, Deanna. And they are both experts in their individual fields, and I've learned quite a lot from them. However, there's a problem. Although being experts in their field, they don't know enough about each other's field. And often when they try to solve brewing problems together, they end up talking past each other. So what we need is someone like me. We need a brewing chemist, a trained scientist that has an understanding of both the science and the brewing field. So with that knowledge, brewing chemists can actually analyze and help brewers solve advanced quality control questions, such as detecting and identifying flavor compounds in beer through mass spectrometry. So let me give you guys an example of what a brewing chemist can do. So let's say we make an Indian pale ale, really hyped up right now, high in demand, costs a lot of money because it requires lots of hops to make. And because it's so high in demand, we brew it on Mondays and Tuesdays and every other day of the week. And we brew it on Monday and on Tuesday. And after 2 weeks of fermentation, we are tasting it and we realize that the beer that we brewed on Monday, beer A, does not taste as the one that we brewed on Tuesday, beer B. In fact, beer A is way more bitter than beer B, and this happened although we use the same recipe. So I'm now tasked to figure out why beer A is different from beer B. And as a brewing chemist, I understand how isoalpha acids work. So my first intuition is that I want to measure the isoalpha acids in our two different beers. And I throw a sample of the beers into a UV vis and I measure the International Bitter Unit Units, the IBU, which is basically just a rough number that relates isoalpha acids and bitterness with each other. And I find that beer A is much more bitter than beer B. Okay, we already sort of knew that. But now I want to take this a little bit further. I want to investigate why were there more isoalpha acids in beer A and in beer B. So I get some samples from the hops that we used. Hops A, which is the one that we use for hops A, and hops B that we use for beer B. And these hops are the same. They're the same variety of hops and were produced by the same farmer. So naturally, we would assume that they sort of have the same chemical composition. What I will do now is I will throw them into my HPLC and I get these glorious spectras. And ta-da, what I see is that the alpha acid peak for hops A is much, much greater than the alpha acids peak for hops B. Same with the hop oils. And I finally found my problem. Apparently, although the hops comes from the same farmer and should be the same, it's actually not the same. This could be due to multiple reasons. But the important thing is we found our problem. So what we learned from this is that we have to test before we brew. And really big companies are really, really good at that because they have enough resources. And smaller breweries actually cannot do as much testing simply because they don't have the resources. But that doesn't mean that small breweries cannot make good beer. And I want to give you guys an example where we really should have tested ingredients before we brewed, or at least looked at them. So through my summer internship last summer at McFleshman's, we were making this nice beer known as 547, which is a West Coast double APA, and it was in a really high demand. So we really had to make this beer quite often. And this is roughly how it's supposed to look like. It has this nice pale color. And after a long brew day, we looked at the beer that we just made, and we realized that our beer looked more like this. It had a really nice reddish color, but clearly this is not what we were supposed to make. So we had to a little bit investigate why the color was different and why also the taste was slightly off. So this is the malt that we would normally use for making this beer, and it's called pale malt because it results in this nice pale color. And we went and looked at the bags and saw that there was a couple of grains left in there. And we saw that a couple of the grains actually more looked like this. They had like this darker color, and they were in fact roasted malt. And just a small amount of contamination of our normal malt resulted in this drastic change in the color and flavor of the beer. And this really is an example of the problems that brewers and the quality control teams and breweries face every day. But on top of that, there are even bigger problems that breweries are facing, which aren't that easy to solve. And one of these big problems is climate change. So 3 out of the 4 ingredients that we are using for making beer are highly impacted by climate change. Water, obviously, if it gets warmer, less water. And already today, there's breweries in Southern California that are highly impacted by restrictions on how much water they can use to the droughts occurring in California. And this really hits small breweries very hard because they're very inefficient when it comes to their water usage. On the other hand, we have malt and hops, which both come from plants. And farmers are highly dependent on optimal growth conditions for making good products. And research from the University of Nebraska actually suggests that by having increasing temperatures due to climate change, we could potentially see a difference in the amino acid composition of our malt. Now, looking back, remember the Maillard reaction? If we have a change in the amino acid compositions, we might end up having different Maillard products, resulting in different tasting beer, basically. So what can we do trying to help the brewing industry? So obviously, we can always try to improve our quality control methods. We can come up with better or new methods, such that we are better monitoring the ingredients and trying to detect, even with tiny changes in them, that could negatively impact the beer that we make. On the other hand, we could also make better ingredients, such as genetically modified hops and malt. And we have done that in the past. We have produced genetically modified barley. The problem with that is that it takes quite long to make it. And some crazy scientists from California actually come up with a way, way cooler alternative to GMO hops and malt, which is the genetic modification of yeast. So what these scientists did is that they used the gene that encodes for the hop oils that comes from the hop plant, and they added it into the yeast genome. So now we have yeast that can actually produce the hop oils during the fermentation. And essentially how this looks like is that we have yeast and it consumes the sugar and produces ethanol, but it also sort of poops out these hop oils during the fermentation, resulting in hoppy flavored beer without adding hops to it. And the very significant thing of this is that by not needing to add hops to the beer to make it hoppy, we can drastically decrease the water usage of the brewing industry simply because cultivating hops requires large amount of water. And this would be a great alternative to make brewing sort of more climate friendly. And although Graham told me to not read off the title of the slide, I will do it. What comes in the future? So, although we aren't really sure what's going to happen next, I can tell you that the brewing world is really ready to deal with any future problems. And brewers in the past have been adapting very well to any challenges. The brewing field is very open to try out new things such as GMO yeast, and there's lots of research going on that potentially could impact or revolutionize the brewing fields. And they probably will find a solution to problems such as how to brew on a desert planet. And this is where I will really end my talk. I want to thank Deanna, Allison, Graham, Rachel, Stefan, and Mike for these wonderful 4 years, for their advice and all of the classes I've taken with them. I want to thank my chemistry classmates for always being so supportive. I want to thank DMART for always helping me out in the lab and being there basically all the time. I want to thank Bobby and Shane and the rest of McFleshmans for my wonderful internship at McFleshmans. I want to thank the Equal Opportunity Fund for funding. And I want to thank my family and friends for their support. And thank you very much. Questions?
So I think as we move to the question portion, feel free to unmute yourself and ask a question, or you can put it in the chat.
Wow. Echt stolz. Der hat jetzt 40 Minuten.
Mama, kannst du dich, Dankeschön.
Any questions? I have one. So when you talk about the GMO yeast, it produces the terpenes, right? But it's not producing the isoalpha acid. So how would it just be less hops, or how would you introduce the isoalpha acids part?
It probably would end up being less hops than we would normally use. But potentially, if they figure it out, they could also introduce the isoalpha acid genes into the yeast and trying to figure out how the yeast could potentially also make these compounds.
I'll do a comment and a question. Hey, Vince, first of all, you do fit that Venn diagram very, very well. Honored and a pleasure to have you work with McFleshman's, and hope I can continue helping you do whatever's next in your career. Uh, I guess I had a comment, like I said, slash a question here regarding how the industry views. It seems as though they're reacting well to climate change. I'm wondering, relating to your GMO comments, if maybe the industry would let go of some dogmatic views, such as, do we even need to boil? So as to maybe save some water and energy and so forth in that kind of decision making. Not really a question so much as just maybe you can elaborate on where you think it's going and how you think your views might fit there.
Yeah, I think it really depends on what scale we are talking about. Because a small brewery like McFleshman's relatively uses not as much or not even close as much water to like someone like Miller Lite. So adding GMO yeast would really be helpful for really, really big breweries such as Miller Lite or Anheuser-Busch. On small scale, it might actually be not like the perfect solution just because GMO yeast is going to be comparative with like fairly expensive compared to normal yeast. So that's definitely something that smaller breweries would have to think about.
You mentioned that you were interested in brewing and chemistry kind of separately before kind of tying the connections between them. How has like forming those like connections through your own work changed the way that you view each of them?
That's a good question. So I would say that chemistry, like I know brewing is like the nice part, and trying to understand what happens on a chemical scale is actually very frustrating. My work on the HPLC did not work out as it was supposed to be at all. It was much, much harder than that. So I think that my views have changed by seeing brewing as really like a cool thing that we have managed to sort of like perfect without even knowing what's happening. And then the chemistry is coming in later. And now we're trying to understand the reasons why things are actually working out and how we can slightly optimize the production of beer. But again, we sort of have already perfected it before chemistry even existed, or before the field of chemistry even existed. Any other questions for me?
So you talked about that one instance that you had when working at McFleshman's where you had the intent of making one beer, but then made another one. And I was just kind of curious, like if there are any instances that you know of where like a really famous beer was made accidentally, where it was like a really good beer that they didn't intend to make. I don't know.
Let me head it off and say that that beer in fact is now part of our lineup. So it's not on the large scale, but there it is.
Cool.
That's one example. But I know you have to think about how beer actually, like where it's coming from. So most people believe that it originates from somewhere from the Middle East. And it was basically just like a very lucky accident and someone of having some grain and some water and it accidentally fermented and then they drank it and were like, oh yeah, this is great. So basically the whole beer, all of the beer is basically was created through this lucky accident like a couple of thousand years ago in Egypt.
Any other questions? Okay. Well, I would like to thank everyone for joining us, and then let's give Vincent a round of applause and thank him for his lovely talk. And I hope to see you all later next week as I think Max goes next on Tuesday. So thank you all. Have a lovely weekend.